Hey everyone, welcome back to the series. We are at video 7. If you've been sticking with me this far, you've basically completed a college-level course in operating systems and storage engines. We've been down in the basement of the stack for a while. We talked about electrons and flash pages and the B-tree and the write-ahead log. We've built a really solid mental model of how a single machine persists truth. But today, we are going to break that machine. I want to start with a concept that I think is really important for engineers to internalize. It's the difference between software infinity and hardware reality. When you open up your IDE, VS Code, or whatever, and you write a for loop or you instantiate a class, you feel like you have infinite space. You can create as many objects as you want. You can write as much data as you want. The abstraction of the software tells you that resources are limitless. But they aren't. We live in a physical universe, and in this universe, we have constraints: speed of light, thermal dynamics, the density of silicon. Up until now, in your career or in this course, you've probably been operating under the assumption that the database is this magical, singular box. You send it data, it keeps it safe. You ask for data, it gives it back. But what happens when that box fills up? I don't just mean the hard drive fills up. I mean the IOPS fill up, the CPU fills up. The network card physically cannot accept another packet. This is the moment where system design actually begins. Before this, you're just building an app. After this, you are building an architecture. Today, we are talking about sharding. And I want to be clear, sharding is pain. Sharding is complexity. Sharding is the point where you stop sleeping soundly at night, because now, instead of one thing that can break, you have 100 things that can break, and they can break in weird, partial ways. But if you want to build Google or Facebook or Uber or even a moderately successful SaaS product, you have to master this. You have to learn how to take the truth and split it into pieces. Let's establish the problem space. Imagine you have a startup. It's a simple app. Let's say it's a note-taking app. You start with one database server. Maybe it's a Postgres instance on AWS, a little T3 micro. It costs you $10 a month. You have 100 users. The database is asleep 99% of the time. Then you get featured on Hacker News. Suddenly you have 10,000 users. The CPU spikes, the latency goes up. What do? You do the most logical, rational thing an engineer can do. You pay Bezos more money. You click a button in the AWS console and you upgrade that T3 micro to an M5 large. Boom, the CPU drops, the latency vanishes. You feel like a genius. This strategy is called vertical scaling, or scaling up. It's great because you don't have to change a single line of your code. Your application doesn't know the server got bigger. It just knows the database is faster. You can keep doing this for a long time. You can go to an X large, a 2X large, a 24X large. You can buy a machine with 4 terabytes of RAM. You can buy a machine with 100 CPU cores. But eventually, and this is the first principle of scale, physics wins. There is a limit to how big a single computer can be. You cannot buy a processor with 10,000 cores. It doesn't exist. You cannot attach 500 petabytes of NVMe storage to a single motherboard. The bus bandwidth, the literal copper wires on the board, cannot handle the traffic. And even if you could, the cost becomes exponential. A server that is twice as fast doesn't cost twice as much. It costs 5 times as much. You hit a point of diminishing returns where you are paying millions of dollars for a machine that is barely keeping up. This is the vertical wall. When you hit this wall, if you try to push harder, your database falls over. It crashes. And when a 4 terabyte RAM database crashes, it takes an hour to restart because it has to read the transaction logs. That's an hour of downtime. That's your business dying. So we need a different approach. We need horizontal scaling. Instead of buying one supercomputer, we buy 1,000 cheap commodity computers. We buy garbage servers. and we tie them together to act like one giant brain. If you have 1,000 servers, your theoretical limit is basically infinite. If you need more space, you just add another cheap server. But here is the catch. How do you store one dataset on 1,000 machines? If I save my user profile, which of the 1,000 machines does it go to? And more importantly, when I come back 5 minutes later, how does the system know which machine to look in? This is the art of sharding. I want to give you a mental model. Imagine a library, a really, really big library, the Library of Congress. They have millions of books. They can't put all those books on one shelf, so they have thousands of shelves. If you walk in and say, "I want the book The Great Gatsby," you don't start at the first shelf and look at every single book until you find it. That would take a lifetime. That's an O of N search. We want O of 1. You go to the index cards, the catalog. You look up Fitzgerald. The card says, Room 3, Aisle 4, Shelf B. You walk directly there. In sharding, we have the same components. The books are your rows of data. The shelves are your physical database servers. We call them shards. And the catalog, well, that's the tricky part. We need a component in our architecture called the router. Sometimes this router is a smart library inside your application code. Sometimes it's a standalone proxy server. But its job is simple. It takes a query and it decides which shard to send it to. To make this decision, it needs a shard key. This is the most critical decision you will make. The shard key is the piece of data we use to slice the world. Common examples are user ID. All of Andre's data goes to shard 1. Tenant ID. All of company X's data goes to shard 2. Geolocation. All European users go to shard 3. Time. All data from 2023 goes to shard 4. If you pick the wrong shard key, your system will implode. I'm not exaggerating. I've seen companies fail because they picked the wrong key. Let's explore why. Let's look at the 2 main ways to organize the shelves. The first strategy is called range-based sharding. This is exactly how a library works. Authors A through D go to shelf 1. Authors E through H go to shelf 2. In database terms, you define ranges of your shard key. Shard 1, user IDs 1 to 1 million. Shard 2, user IDs 1 million to 2 million. This feels very natural to us as humans. We like order. We like things to be sorted. And range-based sharding has a superpower: range queries. If your boss comes to you and says, "Hey, I need a report of all users who signed up between ID 1.5 million and 1.6 million, you know exactly where to go. You go to shard 2. You scan that one server. This is efficient. It preserves data locality. But range-based sharding has a fatal flaw. A flaw based in the chaotic nature of the real world. Data is rarely uniform. Let's go back to the library. Imagine you split the library by the first letter of the author's name. Shelf 1, A through M. Shelf 2, N through Z. That's half the alphabet each. Sounds fair, right? But think about it. How many names start with S? Smith, Stevenson, Shakespeare? Tons. How many names start with X or Z? Very few. Shelf 1 is going to be overflowing. Books will be piling up on the floor. Shelf 2 is going to be half empty. In a database, this is called data skew, and it leads to hotspots. Let's look at a real-world example. Suppose you shard by creation date. This is very common for logs. Shard 1, January data. Shard 2, February data. Shard 3, March data. It's currently March. Where are all the writes going? 100% of the writes are going to Shard 3. Shard 1 and Shard 2 are just sitting there, holding old data, doing absolutely nothing. You have a cluster of 3 machines, but you only have the write throughput of 1 machine. You haven't scaled writes at all. You've just increased your storage capacity. This is the hot tail problem. For a high write system, range-based sharding is usually a trap. So how do we fix the skew? How do we ensure that every shelf has exactly the same number of books down to the millimeter? We stop trying to be organized and we start using controlled chaos. We use hash-based sharding. Here's the recipe. Take your shard key, for example, user ID 12345, pass it through a hash function like MD53 or CRC32. Recall from video 4, a hash function takes an input and turns it into a pseudo-random number. Hash of 12345 becomes 894032. Take that large number and perform a modulo operation against the number of servers you have. Let's say you have 4 servers. 894032 modulo 4 equals 0, so user 12345 goes to server 0. Now let's take the next user, user 12346. In range sharding, this user would definitely be right next to the previous one, but in hash sharding, hash of 12346 becomes 112953. 112953 modulo 4 equals 1. User 12346 goes to server 1. Do you see what happened? Sequential users who probably signed up at the same time are scattered to different servers. The hash function acts like a dealer in a card game, shuffling the deck and dealing the cards out. One for you, one for you, one for you. This guarantees a uniform distribution. It doesn't matter if everyone's name starts with S, the hash of Smith and the hash of Stevenson will be totally different numbers. This solves the hotspot problem. All your servers will be equally busy. You have achieved true load balancing. This sounds perfect. And for a long time, this was the gold standard. Memcad uses this, early databases use this. But there's always a but. Hash-based sharding has a hidden nightmare, a nightmare that reveals itself only when you try to grow.
Let's simulate a growth event. You have 4 servers, n equals 4. Your mapping logic is hash of key modulo 4. Everything is running smoothly. Your servers are 70% full. You decide to add more capacity. You buy a 5th server. Now n equals 5. You update your router code. Hash of key modulo 5. Let's look at the math. Take a key, say key A. Hash of A is 10. Old system, 10 modulo 4 is 2, server 2. New system, 10 modulo 5 is 0, server 0. It moved. Take key B. Hash of B is 11. Old system, 11 modulo 4 is 3, server 3. New system, 11 modulo 5 is 1, server 1. It moved. Take key C. Hash of C is 12. Old system, 12 modulo 4 is 0, server 0. New system, 12 modulo 5 is 2, server 2. It moved. In fact, if you run the simulation, when you go from n to n plus 1, almost every single key in your entire database has to move to a new server. Mathematically, the percentage of keys that move is n minus 1 divided by n. If you have 5 servers, 80% of data moves. If you have 100 servers, 99% of data moves. This is a catastrophe. Imagine you have 100 terabytes of data. You add one server and suddenly 80 terabytes of data starts flying across your network cables. Your network bandwidth is saturated. Your disk I/O is saturated reading and writing data. Your CPU is pegged. And while this is happening, your requests are failing because the router looks for key A on server 2, but it's currently being copied to server 0, and it's not there yet. This is the Resharding Storm. It basically means you cannot scale up without taking downtime. And if your goal was infinite horizontal scale, this is a massive failure. So how do we fix this? How do we add a server and only move the tiniest amount of data necessary? We need to change our geometry. We need to move from a straight line to a circle. We need consistent hashing. This algorithm is one of the most beautiful ideas in distributed systems. It was developed at MIT in the late 90s, and it powers basically everything you use today: Cassandra, DynamoDB, Discord, React, Akamai. Here is the mental model. I want you to imagine a circle, a ring. This ring represents the entire output range of your hash function. If you are using SHA-1, the output is a 160-bit integer, so the top of the ring, 12 o'clock, is 0. The bottom of the ring is 2 to the power of 160, and it wraps around. Step 1. Place the servers. We take our servers, server A, server B, server C, and we hash them. Hash of server A maps to a point on the ring, let's say 12 o'clock. Hash of server B maps to 4 o'clock. Hash of server C maps to 8 o'clock. These are physically located on the ring. Step 2. Place the data. Now, when a write comes in for user 1234, we hash the key. It maps to a point on the ring, let's say 2 o'clock. Step 3. The walk. To find out who owns that data, the rule is simple. Walk clockwise. Start at the data point, 2 o'clock, and walk around the ring until you hit a server. In this case, we walk from 2 o'clock and we hit server B at 4 o'clock. So server B owns user 1234. This seems similar to the modulo approach, right? But watch what happens when we scale. Step 4. Adding a node. We bring in server D. We hash it. Let's say it lands at 2 o'clock exactly. We place it on the ring between server A at 12 o'clock and server B at 4 o'clock. Now, let's look at the data again. User 1234 is at 2 o'clock. Before, we walked clockwise and hit server B. Now, we walk clockwise and we hit server D. So, server D steals that user from server B. But what about a user at 5 o'clock? We walk clockwise, we hit server C. That hasn't changed. What about a user at 10 o'clock? We walk clockwise and we hit server A. That hasn't changed. By adding server D, the only data that moved is the data that sits in the arc between server A and the new server D. Everything else in the universe stays exactly where it is. On average, if you have n servers and you add 1, only 1 divided by n of the data moves. If you have 100 servers, only 1% of the data moves. This is magic. It means you can add a server to a live cluster and the background copy is tiny. It doesn't crash the network. It doesn't overload the CPU. It turns scaling from a traumatic event into a non-event.
Now, if you implement consistent hashing exactly as I just described, you might run into a small problem. Probability is messy. When you hash 3 servers, they might not land perfectly at 12, 4, and 8. They might land at 12, 1, and 2. This would mean server C at 2 o'clock handles almost the entire ring, while A and B handle tiny slices. This is imbalanced. The solution, vNodes. To fix this, we use a trick called virtual nodes, or vNodes. We don't just put server A on the ring, we pretend server A is actually 100 different servers. We create labels, server A1, server A2, all the way to server 100. We hash all of them. Now, server A exists at 100 different random spots on the ring. We do the same for server B and C. Now the ring is covered in hundreds of dots. Because of the law of large numbers, these dots will be mixed evenly. Server A will own tiny slices all over the ring. Server B will own tiny slices all over the ring. This ensures that the load is perfectly balanced. So, consistent hashing solves the distribution of keys, but there is one specific scenario that breaks every sharding strategy we have discussed. It's the celebrity problem, or technically the hot key. Imagine you are building Twitter. You shard by user ID. For me, Andre, I have a few followers. When I tweet, the system writes the tweet to my shard. It's a tiny blip. But then Justin Bieber tweets, or Elon Musk. They have 100 million followers. Depending on your architecture, that single tweet event might trigger millions of notifications. Or imagine a vote counter for a viral TV show. Everyone is hitting the vote button for candidate A. Millions of requests are coming in for one specific key. Key equals candidate A _ votes. Even with consistent hashing, that key lives on one physical server. It doesn't matter if you have 10,000 servers in your cluster. If that one key is getting 50,000 writes per second, that one physical server is going to melt. The disk queue will fill up, the CPU will hit 100%, the server will crash. So how do we fix this? We have to create artificial sharding. We have to split the key itself. Let's look at the vote counter example. Instead of writing to candidate A, we modify our application code to append a random number to the key. We define a split factor of, say, 10. When a user votes, we randomly pick a key between candidate A0 and candidate A9. We increment that specific subkey. Because these are different keys, the consistent hashing ring sends them to different servers. Candidate A0 goes to server 1. Candidate A1 goes to server 5. We have successfully spread the write load across 10 machines. But, and this is the recurring theme of system design, what did we lose? We lost read performance. When we want to know the total votes, we can't just look up candidate A anymore. That key doesn't exist. We have to ask the database for candidate A0, candidate A1, all the way to 9. We have to do 10 reads. And then, inside our application, we have to sum them up. This is read-write amplification. To make writes 10 times faster, we made reads 10 times slower. If you have a heavy write workload, this is a good trade. If not, it might be a disaster. There is one other subtle implementation detail that trips up a lot of engineers when they move from a single DB to a sharded cluster: IDs. In a normal SQL database, you use auto-increment. The database keeps a counter. It guarantees uniqueness. But in a sharded system, there is no central counter. If shard 1 creates a user and shard 2 creates a user at the exact same time, they can't check with each other. Hey, did you use ID 500 yet? That coordination would be too slow. If they both use ID 500, you have a collision, data corruption. So you need a way to generate IDs that are globally unique without coordination. Naive approach, UUIDs. You know these. F47AC10B, huge random strings. They are unique, but remember video 5? The B tree. B trees hate random data. If your primary key is random, the database has to insert the new row in a random spot in the middle of the B tree. This requires loading a random page from disk. This is random write I/O. It is slow. We want sequential write I/O. We want to append to the end of the B tree. So we need an ID that is unique and sortable. The industry standard solution for this is the Snowflake ID. It was invented by Twitter. It's a 64-bit integer, but it's not just a number, it's a structure. Tech specs, fast and rhythmical. Bit 0, sign bit, unused. Bits 1 through 41, timestamp, milliseconds since a custom epoch. This gives us 69 years of IDs. Bits 42 to 51, machine ID, configured on each server. This allows 1024 shards. Bits 52 to 63, sequence number, a local counter that resets every millisecond. Because the timestamp is at the front, the resulting integers are always increasing over time. If I generate an ID now and you generate one 5 minutes later, yours will be numerically larger. This makes the B tree happy. It can just append the data. Because the machine ID is in the middle, two different servers can never generate the same ID. This ensures uniqueness without talking to each other. If you're building a distributed system, stop using UUID v4. Use ULI or Snowflake IDs. Your database will thank you. Okay, we have the theory. We know we want consistent hashing. We know we need Snowflake IDs. But how do we get there? You currently have a massive single Postgres database. It's 90% full. Users are hitting it every second. How do you split it into 4 shards without stopping the app? If you propose a maintenance window to your CEO, hey, can we shut down for 48 hours to migrate data? You might get laughed out of the room. In 2026, downtime is not acceptable. So we need to perform an online migration. This is a surgical operation. It's like performing a heart transplant while the patient is running a marathon. Here is the 4-step playbook that every senior engineer should know. Phase 1, double writes. You modify your application code. Currently, it writes to db_old. You change it to write to db_old and db_new, the sharded cluster. But here is the key. The write to db_new is best effort. You wrap it in a try-catch block. If it fails, you log a warning, but you do not fail the user's request. db_old is still the authority. Now, every new piece of data is going to both places, but db_new is missing all the history. Phase 2. Backfill. You write a script, a worker. It iterates through db_old row by row. It reads a row and writes it to db_new. But there is a race condition here. What if the worker reads user A, version 1, but at the exact same moment the user updates their profile to version 2 via the dual write? If the worker writes version 1 after the dual write writes version 2, you have overwritten new data with old data. You have caused data loss. To fix this, you need timestamps or version numbers. The write to db_new must be conditional. Only update this row if the timestamp of the incoming data is newer than what is already on disk. Phase 3. Verification, the paranoia phase. Once the backfill is done, you might think you're ready. You are not. You need to verify. You write another script. It picks random users. It reads from db_old and db_new and compares them. If they don't match exactly, something is wrong. Fix the bug, run the backfill again. Do not proceed until you have 100% consistency. Phase 4. The read switch. Now we flip the switch. You use a feature flag. You configure the app to read from db_new. But, and this is critical, you keep writing to both. Why? Because if db_new explodes, maybe you configured the indexes wrong, you can instantly flip the flag back to db_old. Since db_old has all the latest writes, you have zero data loss. It's a safe rollback. Phase 5. The success. The write switch. You let the system run for a week. You watch the dashboards. If everything is stable, you remove the dual write code. You decommission db_old. You pop the champagne. This pattern, dual write, backfill, verify, switch, is the universal pattern for data migration. Whether you're moving from SQL to NoSQL, or monolith to microservices, or sharding, this is how you do it. I want to close with a reality check. I've spent this whole video telling you how to shard, but my best advice to you is don't. Or at least don't do it until you absolutely have to. Sharding is not a feature, it is a necessary evil. Once you shard, you lose so many nice things. You lose ACID transactions across shards. You lose joins. You have to fetch the user, then fetch the orders and join them in your application code. You lose operational simplicity. Instead of backing up 1 DB, you have to back up 100. Complexity is the tax you pay for scale. So before you shard, ask yourself, can I just delete old data? Can I optimize my SQL queries? Can I add a caching layer, Redis? Can I just buy a bigger server? Only when you have exhausted every other option should you reach for the sharding knife. So that's it for video 7. We have officially broken the single machine. We have distributed our truth across a cluster. We've learned about the limits of vertical scaling, range sharding versus hash sharding, consistent hashing, and zero downtime migrations. But we've opened a Pandora's box. Now that our data is on different machines, connected by unreliable network cables, what happens when the network fails? If Shard 1 cannot talk to Shard 2, is the system down, or can we keep writing? If we keep writing, are we creating conflicts? This leads us to the most famous theorem in distributed systems, the CAP theorem. Consistency, availability, partition tolerance. People say, pick 2. In the next video, I'm going to tell you why that is a lie. You don't get to pick 2. You get to pick 1, and the other one is forced upon you by physics. We're going to explore the trade-offs of the distributed mind. I'll see you in video 8.